Hi there. My name is Geoffrey Thun, and this evening I wanted to talk about some work that my research group, RVTR, along with Kathy Velikov, my partner, has been developing across a range of scales, from material, system development, complex, large-scale urban design proposals that try to integrate a range of perspectives that really derive from an interest in complex systems, whether that relates to issues of emergence, and the kind of principles around networked systems in the urban domain, to ideas of embedding sensing and responsiveness into artifacts at the scale of the building envelope. Northhouse is an early prototype project for a net energy producing, solar powered building that couples solar thermal and photovoltaic surfaces with an idea of demonstrating 75% glazing in a net energy positive building in a northern climate, which is actually kind of unheard of. And in order to pursue that, we look at using adaptive, responsive exterior shading coupled with highly insulated glazing systems, and in modifying the internal storage capacity of the building with phase change materials. Central to operating the system is a complex control logic that allows individuals to operate the system with gradient controls, such as a dimmer that you might be familiar with, but across each aspect of the project, and effectively interface with something that, although it's designed to optimize energy efficiency, produces feedback with the user. So for example, touch controls change color when one makes a selection that produces a negative energy output. Quantified feedback is provided in terms of energy performance and dollar impacts. And haptic cues are used to produce walls that glow softly when the building is performing well as a way to shape behavior. We then think about models. How could we reduce the amount of mechanical systems required to produce a desirable indoor air quality? In this case, we're using microsensing to sense through infrared sensing human occupancy coupled with CO2 and VOC indoor air quality sensing, to provide only on-demand delivery of indoor air quality, and also only on-demand delivery of light. In another project, we ask, how do we reduce the amount of mass and material required to deliver what we think of as a common transparent system? You might call it a window. And here we're using lightweight ETFE films to produce a series of irregular shaped geometries that hug and bundle together when pressurized pneumatically to produce a thick insulating assembly that allows for light transference, and through air-based actuation can allow air to transfer through the envelope. A lot of our work tries to lightweight material systems and take this principle of physical adaptation and transformation with lightweight energetic actuation and minimize material costs. This project is looking at a kinetic system that uses a TPE or polymer-based assembly to try to just simply define a volume that can dynamically change over time using cable-actuated control systems. And in a lot of the work we work on, we end up having to produce our own material systems, develop design tools, computational design tools that talk to fabrication devices, in this case an industrial robot with a custom TPE extrusion head on it, in order to kind of develop the kind of material systems and assemblies themselves, and then that design tool also becomes the control logic for operating the dynamic performance of the system. More recently, in some other work, we've been looking at questions about how do you transform the envelope and change the way thermal energy works across the envelope. So we're using absorbers on the exterior of wall assemblies to change the delta T across the assembly in order to kind of effectively reverse the heat flow effect in a winter condition. And we're using dynamic shading or custom fabricated static shading, in fact, to reduce those loads in the summer. So the image you see here is using a genetic algorithm to calculate, after looking at the irradiation across the surface of the exterior geometry of the building, a precise set of geometries from which we would use to robotically fabricate the shading device. At the large scale of the region, in a totally different scale of operation, we look at how to apprehend the complex interreactions, in this case looking at the Great Lakes megaregion, which we would define as both an economic zone through the RPA's thinking as well as a watershed. And we're trying to make a series of other sheds that define the complex interactions of systems within the region. The energy part of this is projecting a future for the region where the 320 gigawatts of offshore available renewable wind energy is utilized to produce profits that reimagine new social infrastructures for the region, shared by all. A fairly radical idea if you're following contemporary politics. In a lot of the work we do, we also end up developing installations and exhibitions that translate some of the thinking or demonstrate the artifacts to a broader constituency, and you can buy a book about that. These were some points that I was going to suggest design research is working on. And then lastly, I'll just make a plug for an enterprise we've been developing across the university called the Urban Collaboratory, which is an outward-facing entity intended to translate research from emerging smart city technology space, but also from the energy space, outward to city as client model. Integrating design prototyping is another way to think about how we would move our research out of the university and into the public domain.